Howdy, Calc AB. Welcome back. Good to see you all again. It's been a little while since we had a video. We are starting chapter 5. We're back. We're going into new material. Chapter 5 is all about natural logarithm, log base E, exponentials, differential equations. So there's lots of stuff in here. We're going to open up a whole new set of functions for us to do calculus with. They're called transcendental functions. And I think what you're going to see here is that there's some more memorization that come in your way, some things that you need to remember how to do. And there's a whole list of formulas. If you haven't found it already, in the front cover of your textbook, there's like 22 derivative formulas, 19 integration formulas. We are going to complete that list so that those are all the formulas that you're going to need to commit to memory. Unfortunately, for those of you taking the AP exam, you don't get any of that when you take the test. They don't give you anything. So buckle up and get ready to go. Chapter 5 is a lot, and we don't have a lot of time to get through it. So here we go. What I'm taking on section 5.1 here, and what this is all about, it's about logarithms. Now, before I get into the stuff in chapter 5, I thought we should probably spend a moment reviewing a little bit of the logarithm work that you've already done. Just because, well, I know that sometimes when, Mr. Davis or Mr. Gann or whoever you had for pre-calc was telling you, hey, you really do need to know this stuff, you didn't believe them, and you should have. So let's talk about logarithm rules. And there's a few rules in here that we know, and actually they're very closely related to some exponential rules we know. So for example, let's write exponential rules up here too. Exponential rules. There we go. Woo, a little trouble with the typing here today. In exponents, let's start with an easy one. When you're multiplying, if you have a to the n and you multiply by a to the m, right? What do you do with your powers? You add them. If you're doing a to the n and you're dividing by a to the m, what do you do with your powers? You subtract them. And if you have a to the n power and you raise that whole thing to the m power, what do you do with your powers? You multiply them. Right. Okay, well, there are corresponding rules in logarithm land that go with each one of these rules. Why? Why do they match up so well? Because what is a logarithm, right? What is it? It just means exponent, right? So we'll see in a minute when we review logarithms, like what it is, right? But yeah, it literally just means, hey, what exponent do I put on this base number to get my answer, right? So in other words, if you have the logarithm of a times b, right? What do you do with the logarithms? You add them. Just like here, oops, here, well, good enough. You add when you're multiplying. Yeah, we just work with the exponents. Okay, so what about if I'm dividing? What am I doing with my exponents? I'm subtracting them, right? Yeah, that's log A minus log B. You got it. Last one's a little bit weirder, I will admit. Okay, if I have log base A to the nth power, okay, well, that's a power, log of A, it's a power, raised to another power, which is n. So I multiply my powers together, n times log of A. And those are some logarithm rules that we're going to use quite a bit in this chapter. So it's good to review them. Now, I wrote them all with just the word log, without a base number written there, which you probably remember means common log or log base 10. Which is great. Log base 10 is fantastic. Why is it base 10? Well, why do we count in base 10, right? Yeah, exactly. 10 fingers, right? 10 toes, right? If we were on the Simpsons, we'd count in base 8 because, right? Simpsons, they've only got 4, right? Well, 4 and 4, they got 8. So yeah, so where we count 1 through 10, Homer 1, 2, 3, 4, 5, 6, 7, 10, 11, 12, 13, 14, 15, 16, 17, 20. Yeah, exactly. Log base 8. But for us, it doesn't matter what log base number is here. It could be log base. Oh, I probably shouldn't have said B because I had B's in there. Let's take log base R. Yeah, it doesn't matter what R is. It can be any base. Okay. The rules for logarithm are the same. So as we get further into our work this chapter, you're going to see that we're going to invoke a lot of those rules for logarithms. Okay, now there is one very special logarithm that we are going to use a lot. Okay, and you probably remember it. Okay, it's called natural log. Now, anybody know why it's called natural log? Okay. Nope. All right. It's called natural log because the guy who's mostly associated with it. Now, there's other mathematicians, Napier and all these other guys, but there's one particular mathematician, guy named Euler. It uses his number, Euler's number, as the base. Okay. And Euler's number is E. And so these are log base E's, right? And he was studying a lot of natural phenomenon where the rate of change in whatever it was, whether it's a population that's growing or something that's decaying or whatever, it's something that was naturally occurring, right? The base that a lot of them grew according to or decayed according to was this weird number E. It's a transcendental number like pi. Okay, it's not irrational necessarily. I mean, it doesn't repeat and it doesn't terminate, but it's kind of got its own special place. And so we say log base E of, let's say, X. We shorten it because we use it so much. We use ln of X. Now, if you're going, whoa, wait a minute, natural log, why is it ln? That's because, as you could probably guess from his name, Euler, he ain't from around here. He's French. And in French, just like Spanish, you put the adjective after the noun, right? Okay, we say natural log, but in France, they say log naturel. Oui, oui. So it's ln of X. Same thing, just means log. Okay, the base is just this number E. Okay, but that's what it is. Okay, now, where did it come from? Good question. Well, I'm going to introduce you to an integral that heretofore you could not have done. The integral of 1 over x dx. You couldn't do that one, could you? Well, you could try. You could try it. You'd be like, well, wait a minute, Mr. A. Yeah, we could just rewrite that. And then we just use the power rule, right? We'll just add 1 to the power. Oh, that's not good. 1 divided by 0. That is not infinity. Okay, so this doesn't work. Okay, so what does work? Well, that right there, my friends, is the definition of the natural log of x. The natural log of x is the integral from 1 to x of 1 over t dt. That is natural log of x. Perfect. Okay. Yeah. That's how we get natural log. Okay. Which means if you want to take a derivative of natural log of x, guess what? You get 1 over x. And that becomes a very big deal for us as we work our way through this chapter. Okay, that's the definition that we're going to go with for natural log of x. Okay, it is 1 over t dt on the interval 1 to x. Okay, we get natural log of x. Now, more importantly, when we derive natural log of x, we get 1 over x. Yeah, so we're going to be working in derivative land for today. Now, of course, what if we're taking a derivative and there's a u in there? but we're taking a derivative with respect to x. There's a mismatch here, right? See how there's a dx, but there's a u in here. There is an implication, right, that u is actually some function of x. Oh, so how do we derive when there's a function inside of another function? What's that called again? It's been so long. I don't remember the name. Chain rule. That's right. Yeah, when we start taking derivatives with natural logs and there's functions inside of natural logs, we gotta remember our chain rule. Well, that's not so bad, right? I mean, we know it's 1 over u, right, for the natural log. And then the chain rule says, well, now wait, you're not done. Just multiply by the derivative of the inside function, u prime. A lot of times we just shorten this, guys, and we just say u prime over u. Okay, and that is, as I mentioned, we are getting more developed in our list of derivative formulas. Well, if you look at derivative formula number 9 in the front cover of your book, there it is. The derivative with respect to x of natural log of u is u prime over u. Let's try it out with some functions. Yeah, here's an example for you. Okay, example number 1. I want to find the derivative with respect to x of the natural log of 2x. Okay, well, it's u prime over u. What's u? U is the function inside right there. That's u. So what's u prime? 2x derivative. 2 over 2x. Hey, those cancel out. And we just get good old 1 over x, right? Weird. The slope of the natural log curve of 2x is just 1 over x, just like if the 2 wasn't there, right? Think back just a slide ago, right? I said derivative of natural log of x is 1 over x. Doesn't matter if you multiply by a constant inside there. Why is that? Remember those rules for logarithms I gave you just a second ago? When you're multiplying, what are you doing with your exponents? Hey, the natural log of 2 is a constant. And what happens when you derive a constant? You got it. They just derive away. 0 plus 1 over x, which is 1 over x. There you go. Yeah, it's just like adding a constant to the original function 1 over x. And that's not going to change the slope. No, sir. So I like to do it like the top one here, but this is why that works so well. Okay, and the 2's just cancel each other out. All right, now if it's an addition in the middle, well, then it's a little bit different. Okay, here's example number 2. Okay, this time I want to derive with respect to x, the natural log of x squared plus 1. Okay, now there is no distributing a natural log across a binomial. That is not natural log times x squared plus 1. Natural log of x squared plus 1. Okay, don't distribute it. That's not allowed. Okay, you can only split it up if it was a product or a quotient. Okay, so this is just simply going to be the derivative of x squared plus 1, 2x, the plus 1 derives away, over the original function, x squared plus 1. Again, u prime over u. Nice. Okay. Example 3. This one's a little bit harder. I think you guys are ready. That is x times the natural log of x. It's been a while, hasn't it? This is a product of 2 functions. In order to derive a product, you must use the product rule. That's right. So if x is the first function, ln of x is the second function, derivative of the first is 1 times the second function, plus the first times the derivative of the second function. Natural log of x's derivative is 1 over x. Oh, look at that. It's the natural log of x plus 1. Cool, right? Yeah, no problem. Example 5. I know, they're getting harder. Let's see. Oh, yeah. Derivative with respect to x of natural log of x quantity cubed. Oh, see what I did there? I made it another chain rule problem, but this time the natural log is actually the inside function and the cube is the outside function. So when you want to derive these, okay, outside function first, 3 times natural log of x, okay, right? Bring down the power, subtract 1 from the power, then multiply by the derivative of the inside stuff. And simplify it up, you get 3 natural log of x quantity squared all over x, like so. Yeah, so there's lots of different kinds of functions now that we could invoke as long as they have a natural log in them. Example 6. This one, this time I'm gonna say my function is the natural, oops. Yeah, come on. There we go. Natural log of the square root of x plus 1. Now, you're probably going, okay, Ray, you're just throwing us another chain rule problem, and you're right, I am. But I want you to notice something important about this one, okay? Let me go back a couple pages. There's a rule I want you to remember, okay? I want you to remember this rule. Because this rule can help us turn what I just had for our problem into something a lot simpler. Check it out. You see, notice this is actually the natural log of x plus 1 to the 1/2 power. And with that rule for logarithm powers, I can actually bring that 1/2 out front and make it a coefficient. And I get a much simpler way to go with my derivative now, right? You see, by bringing that down and making a constant in front, f prime of x is just 1/2 times the derivative of natural log of x plus 1. Well, x plus 1's derivative is 1 over x plus 1. I think that was a lot easier than the alternative, which was to use the chain rule. Because here we go. Let me show you what would have happened had we done it with the chain rule. Or you could do this. U prime over u. Okay, so there we go, u prime over u. So what's the derivative of x plus 1 to the square root? Oh, okay, it's 1/2 x plus 1 to the negative 1/2 times the derivative of x plus 1, which is 1. Okay, thankfully that was good. Over the square root of x plus 1. You can see the algebra. This x to the plus 1 to the negative 1/2 comes down into the denominator, and you get x plus 1 to the 1/2 times x plus 1 to the 1/2, which is of course x plus 1. But wasn't that a lot easier? I think so. Yeah, in fact, it's so much easier that these properties for logarithms can really help simplify even the most complicated of derivatives that involve natural log. I think you're ready for it. Example 7. The dreaded, the feared, the colossal natural log of x times x squared plus 1 quantity squared over the square root of 2x cubed minus 1. What? I know, it looks tough. It is tough, okay? I do not want to do u prime over u just yet, guys. There's so much we can do here with our rules for logarithms. I mean, just taking the numerator and the denominator apart, right? Oops, there we go. Okay, but I'm not done yet, because the first term here, x times x squared plus 1, that's a product. I'm going to write this a little differently so you guys can see ahead. You already know where I'm going with it, right? Look at these powers here and here, right? Those can come down in front. And now I can just do each one of these terms separately to get my derivative. Use your powers of logarithms, your properties of logarithms to expand your function before you try to derive it, and your life will be so much easier. This problem is so much easier because I split those up. There you go. Is there any reducing or simplifying we could do? Well, sure, we could do this right here. We can multiply that to get 4x. There's a 2 and a 6 that would reduce here. That would be nice, right? Okay. Unless you have some like urgent need to have it be one fraction, though, I wouldn't necessarily go around finding a common denominator, combining these three things together. I think what we have here is just a really nice answer. I know I've talked about it in my class. I'm sure Ms. Hoagie's talked about it with you guys in her classes. If the AP test says take the derivative, we're done. We've taken the derivative. Don't start doing a bunch of algebra. We are so much more likely to make an algebra mistake than a calculus mistake. You just don't want to start messing around with it if you don't have to. Now, if there's for some reason why they want you to simplify it down, then okay, they'll tell you that. The worst case would be if this was a multiple choice prompt and this wasn't one of the answers and they were all single fractions, and you're like, oh, okay, crud. Now I got to go through and figure out what this is one fraction. But I'd say 99% of the time they don't do that. They really don't. They take these answers just as they are. Wasn't that cool? I mean, just expanding with those logarithms. It's so cool, in fact, that you might actually choose to put logarithms into a problem that doesn't have them, because you can take advantage of these same features of logarithms, even if something like example 8 happens to you. This is called logarithmic differentiation. What it means is you're going to take a derivative. You're supposed to find the derivative of y, let's say. We want to find dy dx, and y looks like this. And you're like, oh man, Mr. Ray, why would you do that to us? That's a quotient rule. Can't get away from the quotient rule. It's a chain rule. I mean, I suppose you could turn into a product with a x squared plus 1 to the negative 1/2 in there. But man, all in all, this one is just tough. And so let's do this. Let's bring in a logarithm, even though our problem doesn't have it. I'm going to take the log on both sides. Now, because I've done that, I have to remember something that's really tough. Sometimes first years forget this. you have to derive both sides of the equation. And I'll show you what I mean here in a second. When you're doing logarithmic differentiation, you derive both sides of the equation. We've actually been doing this the whole time. Okay, we've been figuring out what dy dx is. So we've been deriving the left side. We just didn't think of it like, oh, this is an operation that we're doing on both sides of the equation. But now we really do have to think along those terms. So on the left-hand side, what is the derivative with respect to x of the natural log of y? Well, there's a mismatch here, right? Okay. This variable y then is assumed to be some function of x. So we say it's y prime over y. Now, over here on the right-hand side, I'm not going to derive just yet, right? The whole reason I brought this darn logarithm in here in the first place was I want to be able to expand using the properties of logarithms, my original function, so that I can take advantage of the squared can come down in front. It's 2 times natural log x minus 2. It was a quotient, so I know I'm subtracting 2 logarithms. I've got a 1/2 power down here, so I bring down the 1/2, natural log x squared plus 1. And now I can just go through and do my u prime over u. This time, when I derive the right-hand side, there's a variable agreement, so I know it's differentiating with respect to x. Like so. Like so. I get a little canceling here. Okay. And so I'm sitting here at 2 over x minus 2 minus x over x squared plus 1. Now, remember what's on the other side though, right? What's sitting over here on the left-hand side is y prime over y. My task was to find the derivative. Aha. That means I need to figure out what dy dx or y prime is. I don't want to know what y prime over y is. I want to know what y prime is. So I have to multiply by y on both sides. The y's will cancel. And over on this side, guess what I'm going to use for y? You got it. Yeah, right. Y is equal to what? X minus 2 quantity squared over the square root of x plus 1. I knew that from the beginning. It's up here. So bring that guy down here when you bring in y. And now your answer is a nice, somewhat simplified, still kind of complicated, but it's not bad, function that just has dy dx or y prime totally in terms of x, because that's our goal, right? We want to know what the derivative of y is with respect to x. Yeah, it is a great procedure when you have a particularly nasty little function that you're trying to take a derivative of. It's got quotients and chain rules and roots and squares and cubes and everything mixed together. Take a natural log on both sides, expand your really complicated fraction thing with the rules for logarithms, and then take your derivative. I think you'll find that it works pretty well every single time. All right, guys, that's a lot. That was a quick video. Plenty of opportunity to go back through this again, pause it, rewind it, slow it down, whatever you got to do. I know I hit you with those 8 examples really quickly. Just remember, it all comes back to how do we take a derivative with a natural log? Well, oops, one more. Coming from its definition, that's actually pretty easy. As long as you remember the definition of natural log, derivative being 1 over x. All right, guys. hope you had a great weekend. If you're watching this over the weekend, hope you're having a great weekend. And I'll see you guys, for my kids, I'll see you in class on Tuesday. Don't forget, if you're in my class and you want to sign up for a live session, please do so on the Google form. It's not mandatory to sign up. I haven't had a real full class, but I do like to know who's coming. So it'd be great if you would sign up if you want to come in for class in person on Tuesday. All right. Thanks so much, guys. Have a great day.